Hi guys, in this section we will see about future control frame. In GD&T. As the name indicates, future. It is the future controls the, or it is the future what we have to control on a component. How we can able to control the future which is made on a component, right? Future control frame. This is called as a future control frame. This is for positioning a hole. This feature is used for positioning a hole because I am using here position tolerance symbol. As we discussed, there are 14 symbols in GD&T. So depending on the application and depending on the future, we are going to use all these 14 symbols wherever it is required, right? So this is for dimensioning a 20 diameter hole. We know about how to dimension this outer surface. We won't discuss about the outer surface dimension as of now. So we see about how to dimension this 20 diameter hole and how to position this 20 diameter hole, right? So this is the future control frame that we use for dimensioning a circular component. So this indicates future size of the future, means exact diameter of the hole. This indicates size tolerance. As I said, every dimension should have a tolerance. So this can vary up to 21 or dia 19. It can fluctuate, but not beyond this. Right? This is how we have to calculate tolerance here. Then So this is about the future and size tolerance and value. Now fifty. So in the previous section we have seen, or we have taken profile tolerance, general profile tolerance of 2A, B, C like that, and tolerance for this will be pulled from the profile tolerance, right? That is one scenario, and this is a different one. In that case, this feature control frame is not there. Without feature control frame, we can take tolerance from here. But by using a feature control frame, we have to provide tolerance. This is the position. This box can be used for different symbols based on the application. This area, this location. Now we are taking a circular component and defining a position tol. This is the position symbol, right? This is the diameter. This is the 0.2 mmc. That means plus or minus 0.1. Right? So tolerance for this 50 will be taken from here, and tolerance for this 50 will be taken from this G-tol. This is the position tolerance. That means this axis can be shifted plus or minus this value, plus or minus 0.2 with respect to right side or with respect to upward and downward. It can go 50.2 or 49.8. Similarly here also. I am talking about the position of the hole, not the diameter of the hole. Position of the hole can vary 50.2 to 49.8. This position can vary, right? So we have to take this tolerance based on or with respect to datum. With respect to datum A, B and C, we are going to position the hole. This is called as a primary modifier, secondary modifier, tertiary modifier. Right? So we have to position this GD&T based on the datums, and we have qualified or used all the datums in this G-tol. So this is the modifier section. Since A, B, C are taken on the surface, there is no modifier here. If it is M here, we call as a modifier. If it is M here, we call as a modifier. We'll see this one. Now, with the same example, just slightly modified. have taken 0 planes here. To simplify it, either you can take, or it's not mandatory to take 0 planes. In order to explain you a simple concept, I have taken 0 planes. Now this is datum A, and we won't consider about the outer surface dimension as we know that already. I will take this as datum B and this as datum C. In this case, or in this example, I have taken B on the future and C on the future. In the earlier example, I have taken on the surface. You can take anything. It's not a big issue. Suppose I assume that it is 20, 30, something around 10. Here, similarly, there is a plate here, right? On that plate, we are going to make 2 holes of different diameter. It can be the same diameter. Diameter is not an issue, but we are going to make 2 different holes at different location, right? So first I want to make this hole. First I need to fix one surface, datum A. Then I will drill this hole or punch this hole with respect to diameter something around 10 plus or minus 0.5. Now comes the G-tall. Here, since it is a hole, we use position, and since we are positioning the hole, we use a position geometric symbol. Since it is a hole, we use a diameter symbol because it is a circular component. Here, some value, maximum material condition or least material condition. It depends on the material of the part and mating component. So now, as of now, I am taking MMC. Since I know only datum A, because I don't know datum B and C. Since I know datum A, with respect to datum A, I am making this hole. Right? Now, I want to make this hole. And this 0.5 is for positioning. 10 plus or minus 0.5 and 30 plus or minus 0.5. It can vary the position of the hole, and this is called a size tolerance. It can go up to 10.5 or it can go up to beyond 10.5. It's 9.5. It can go up to 10.5 or 9.5. So this is the position tolerance applied for the position of the hole. Now, with rest, I know I have taken this as datum B because this hole is already there. I have made this hole with respect to A datum. Now I am taking B, right? So I will make this surface as datum A and fix it. It's already done while making this hole, and now I am going to fix this hole with respect to datum B, right? And one more direction is arrest. Actually, we have to arrest in 3 directions. Now one is arrest, second is arrest. Based on the first and second, we are going to drill this hole or punch this hole. So for this, again, we are positioning. Since it is a circular diameter, some value, condition A. Now comes modifier. B maximum. Maximum material boundary, similar to maximum material condition. Whenever a datum is taken on the future, if this modifier is applicable. If the datum is taken on the surface, this modifier is not applicable. We are going to give all the datums, right? And this 0.5 is the tolerance for this position and this position. And this 20, as we know, it is the size value and it is the tolerance value or the size tolerance. So this is about the future control frame. What about C? I have taken B, A. There is one more datum to qualify. As I said, all the datum should be qualified. Suppose I have not taken any C. This looks fine. Tolerance for this will be given something. Tolerance for this will be given something. Suppose this tolerance is not there. Then we can take profile of some value A and B only, because there is no datum C. Since it is a simple component, I have not taken datum C. If it is a complex component, if you want, you can take datum C. If you take datum C here on this whole datum C. So in this way, all the datums are arrested, or all the datums are used in the GTOL. So by this, we can control translation motion as well as the orientation. If you take C, this component is fixed. Suppose if I have not taken this C, I know B. I have fixed like this. This surface is fixed and axis is fixed. There is a chance of rotation of this plate like this. There is a chance the plate can rotate or tilt like this. So for that, we can take datum C. Suppose if there is one more feature here, then GTOL. Diameter 0.1 or something, MMC, A, B MMC, and C MMC for this, because we are taking datum A, datum B as well as datum C. So we are qualifying all the datums in this GTOL to fix the component. So this symbol we have to use based on the application. We can use perpendicularity based on the future, defining based on the defining of future. We can use parallelism, circularity, profile, flatness, right? So here this surface should be flat, because we are mating this surface on the other component. If this surface is irregular, we can't. So this should be flat. So in this case, we use flatness symbol, some value with respect to A. This is the flatness symbol. So this surface can go like this. This surface, mating surface, can go like this, can go like this up to 2 mm, +1, -1. Right? This is about the flatness. Similarly, we can use parallelism, perpendicularity, angularity. So depending upon the application. So this is about the future control frame. Right? Hope you understand about this future control frame, and this is used for all the symbols, all the geometric, all the 14 symbols: form, orientation, profile, runout, and location. To control the form, orientation, runout, and location, we use this future control frame differently. Some symbols take datum qualification, some symbols they won't take datums. That means we are going to use datum for some symbols, and we are going to use symbols without datums also. In this case we have used datum. In this case we have used datum. Right? So this is about the future control frame. All the tolerances, before giving any tolerance, we have to know what is the application of the component, what is the next mating component, or onto which component the pre-existing part is going to mate, what is the material of the component, where it is used, that means the application. Then only we can provide tolerance. Without knowing all these things, we can't provide any tolerance. We can give just a dimension. Even though dimension is also not possible, exact dimension is not possible without knowing the entire design or what is the purpose of the component and onto which that component is going to mate, and what is the material of the mating component, whether it can mate into the existing component or not, or whether the second component is going to mate into a third component or not. That means we have to know the complete scenario, complete design of the part or design of the component. Then we can decide tolerance. How much tolerance is applicable in part 1, and when it goes into the part 2, same equivalent tolerance has to be given for part 2, and the same equivalence tolerance is applicable for part 3. Then only the final output will be the perfect. Suppose in part 1 you have given ±1, ±2, 0.5. How it is going to mate? There will be a lot of variations. So this is not at all advised. First we have to study all the components. Then we have to decide how much tolerance we have to use. So this analysis we call as a tolerance stack up. The complete thing we call as a stack up analysis. It involves a lot of calculations. whether the shaft is going to mate onto the hole. If you take maximum material condition for the shaft, is that going to mate into the hole with MMC of the hole or LMC of the hole, or is it going to violate the rules, or is it going to break the component? So all these things will come under stack up analysis. So finally we have to know full picture of component, then only we have to go for sub components, right? So this is about the GD&Ts, tolerances, feature control frame, datums, then only we can manufacture the part with excellent quality. Thank you.